We've talked about inductors and how inductors control current in a DC circuit, where when you turn on an inductor for the first time, it acts like a broken circuit. The inductor resists the change in current of the circuit, but it can't completely fight against it. It loses the battle, and eventually current builds up in the circuit, and once current's established in the circuit, then the inductor just acts like a normal conducting wire. It doesn't resist the flow of current anymore. So that's its behavior in a DC circuit. In an AC circuit, it's a little more complex. In an alternating current circuit, the current is constantly changing. And remember, an inductor, like a solenoid, hates changing current, right? A magnetic field appears to resist the change in current in an inductor. And in an AC circuit, the current is constantly changing, which means that the inductor is constantly resisting the flow of current in an AC circuit. That resistance is called, we don't call it resistance in a AC circuit for an inductor, because resistors provide resistance. But this still is in opposition to the flow of electricity. In AC circuits, we call that reactance. So capacitors and inductors behave differently when placed in an AC power source. So we have a simple inductor circuit here. So we have an alternating current power source. That's what the little sine wave is, a little sinusoidal change of current. Doesn't have to be a sine wave, but that's the most common form of AC current. An inductor here with inductance L. When I plug in this circuit and turn it on, if I were to plot the current shown here in red and the voltage shown in blue as a function of time, and your book has a similar graph, what we see is the two are not in alignment. When the current is at a maximum, the voltage is 0 in all cases. When the current is at a minimum, the voltage is 0. When the voltage is at a maximum, the current is 0. So they're out of phase, we say. They're not in phase with one another. They're out of phase. The voltage is applied and leads the current by 1/4 of a cycle. So the voltage reaches its peak 1/4 of a cycle before the current does. The voltage reaches its minimum before the current does. By a cycle means one complete oscillation, right? One full period of motion of the circuit. The current, remember, in an AC circuit is going back and forth, back and forth, back and forth. So how long does it take to complete one of those cycles? So the voltage is leading the current by 1/4 of a cycle. Well, how do we figure out what the current is in the circuit? Well, I said that the inductor resists changing current, but you can change current in different ways in an AC circuit. You can have rapid change of current, a very quickly oscillating AC circuit, or a very slowly oscillating AC circuit. Well, hopefully it's not too hard to grasp that since inductors hate changing current, the faster you change the current, the more they're going to resist the flow of current. So the RMS current through this inductor is given by the following equation, similar to Ohm's law. The current is equal to the voltage over some value that's an analog to the resistance of the flow of electricity. For a resistor, that would just be R. But we introduce a new term, X sub L. X sub L is called the inductive reactance. So this is the reactance, again, the resistance to the flow of electricity in an AC circuit. Inductive reactance is the resistance due to the inductor. It is given by the equation 2 pi times the frequency of oscillation of the circuit. So, for example, in the US, in the wall outlets you have in your house, the frequency of alternating current oscillates at 60 hertz, or 60 cycles per second. In Europe, it's 50 hertz, 50 cycles per second. But it could be a variety of different values. Depends on the frequency of oscillation and the value of the inductance. So, a big inductor gives you a bigger reactance, a resistance to the flow of electricity, and a faster oscillating AC circuit provides a bigger reactance, a bigger resistance to the flow of electricity. So the faster this oscillates, the harder the inductor pushes against the flow of current, and the more resistance, if you will, it has to the flow of electricity. So this is for an inducting circuit in an AC setup. What about a capacitive circuit in an AC setup? When a capacitor is placed in an AC circuit, as we have drawn here, a similar but slightly different effect occurs as with an inductor. So we have here a plot of the voltage versus current. But you can see now that rather than leading the current, the voltage lags the current, right? The current is shown here in red. When the current is at a minimum, the voltage follows shortly after. When the current is at a maximum, the voltage follows shortly after. So when a sinusoidal voltage source, or an AC voltage source, is applied to a capacitor, as you have here shown a parallel plate capacitor, the voltage follows the current by a quarter of a cycle. It no longer leads the current like it does in the inductance version. So what is the current again? Well, the RMS current is the voltage of the AC source over the capacitive reactance, X sub C. The capacitive reactance, unlike the inductive reactance from earlier in the video, which was equal to 2 pi times F times the inductance value L, you can see that this is 1 over 2 pi times the frequency times the capacitance. It's the inverse. L is replaced with C, obviously, because we're talking about capacitance, not inductance, but it's completely flipped around. It's 1 over the value it was before. Because capacitors behave differently when you apply alternating current voltage. Remember that inductors start off like broken wires in a DC circuit and end like a regular conducting wire. They resist the flow of electricity early on, but later they allow electricity to flow freely. Capacitors are exactly the opposite. When you start charging a capacitor, the current flows freely, but once the capacitor is charged, the current stops. It can't push any more charge onto the capacitor. So, rapid changes in frequency are allowed by a capacitor. Capacitors don't really resist rapid changes, but if the frequency change is really slow, then you have current going in a direction long enough to start charging up the capacitor a significant amount, and the capacitor starts resisting the flow of current. So, the capacitive reactance is proportional to 1 over the frequency, whereas the inductive reactance was proportional to the frequency. So these are what are called filters, if you will, high-pass and low-pass filters. High-frequency signals go through a capacitor easily. Low-frequency signals don't. For the inductor, low-frequency signals go through the inductor easily. High-frequency signals don't. Now, capacitive and inductive reactance, if you remember this equation here, it's similar to Ohm's law, right? Current is voltage over some resistance or resistance analog. So amps is volts over ohms. This has to have units of ohms, the reactance. So the reactance has units of ohms, as does both the capacitive reactance and the inductive reactance, as well as the resistance. So we'll look at next, what if we just place a simple resistor here? Not a capacitor, not an inductor, but a simple resistor. What happens to this setup? When we place a simple resistor in an AC circuit, we see that the current and the voltage are actually in phase with one another. That is, when the current is 0, the voltage is 0. When the current is maximum, the voltage is maximum, and so on. So these two objects are in phase. Unlike the inductive circuit, where the voltage leads the current, or the capacitive circuit, where the voltage lags the current, in a resistive circuit, the voltage and the current are in phase with one another. Now, the current in that circuit is just given by Ohm's law, right? The current is equal to whatever the voltage is divided by the resistance value R. R is in ohms. So this is a simple equation, very similar to what it is for a DC circuit. So we've seen how the current behaves when we have a capacitive circuit and an AC circuit. when we have an inductor placed in an AC circuit, and now when we have a resistor placed in an AC circuit. What happens if we put all three together, right? We've talked about RC circuits already, circuits with resistors and capacitors. We've talked about RL circuits, circuits with resistors and inductors. What about an RLC circuit or an LRC circuit, or however, whatever order you want to put it in? I think your book uses RLC. So, objects with a resistor, a capacitor, and an inductor. Well, we'll look at that in the next lesson.